This is chapter 12, ANOVA. ANOVA is actually short for analysis of variance. This is a very different test than what we've been talking about so far, because the other tests have relied on comparing means, which is very kind of straightforward and intuitive. If there is a difference between the means that is greater than we would expect by chance, then we have evidence of a difference, a statistically significant difference, and it's obvious. It's right there in front of us. This test relies on variances, and if you recall from the beginning of the course, a variance is a measure of variability. It's a measure of how different scores are. It kind of relies on the same logic of the t-test in that the null hypothesis is no different, is the hypothesis of no difference. And in this test, if two groups are if two variances are measuring the same things, they should not be different from each other. But the idea of variances and measuring differences is a little bit difficult. That's what makes standard deviation and variance generally hard statistical concept to understand. But this test makes a lot of sense, and you've got the logical underpinnings for it already. It follows the same steps of hypothesis testing. It just does things a little bit differently. But we'll go through it, and I'm going to do a simplified version of analysis of variance. If you read the chapter, it talks about how to calculate all kinds of different things. We're not going to do that. We're not going to do from the raw data. I want you to understand analysis of variance at a conceptual level. There'll be some calculations, but I want you to focus on the concepts. So, analysis of variance. Imagine we have an experiment, and imagine this is a memory experiment where I have three groups of individuals. This will be, this will be an independent samples kind of situation. So I've got three separate groups of individuals. An analysis of variance is appropriate whenever we have more than three groups of that we're testing, and it works in both independent and dependent correlated repeated measures situations. So anyway, this is a memory experiment. I've got a list of, say, 25 words, and 1/3 of my overall set of volunteers is given instructions to use rote rehearsal, simply repeat the words again and again. The second group is told to use an imagery strategy, and the third group is told to put each word into a sentence. So there's three different memory strategies. This is when analysis of variance would be the preferred test, because anytime you have more than two groups, using a t-test can be a little tedious. We could do this using t-tests, but we run into a problem, right? With three groups, the problem is called probability pyramiding. And let me explain that. If we're doing t-tests, the way to analyze this design would be first, right, a series of t-tests. First, I do R minus I. I can only do two, right, compare two groups at once with a t-test. So I have R minus I as the first test. R versus S, rote versus sentence, as the second. And then the third comparison would be imagery versus sentence. With those three t-tests, I could figure out which one of these is significantly different from the other two. Maybe they're all different from each other. But that would be three separate t-tests. Now remember, when we do a single hypothesis test and we set the level of significance at, say, 0.05, right? That means there's a 0.05 chance of a type 1 error in that particular test. So if I do three separate t-tests in this family to analyze this design, what happens is that level of significance, the probability of a type 1 error, pyramids. It adds up. If it's 0.05 for one test and I do three tests, it's 3 times 0.05. So by repeatedly doing t-tests on a family of groups like this, raises the probability of a type 1 error with each additional test. so that I end up with a design plan or an analysis plan where the chance of one of those tests having a type 1 error is greatly increased. So t-test could be used, but as I said, it kind of gets ugly and generally increases the chance of a type 1 error. Analysis of variance deals with this by a completely different approach. And this is sometimes called the F test, and it uses the F statistic. We've used Z's, we've used T's, now we're going to use something called the F. And this was created by another statistician who saw the probability pyramiding problem and found a way around it. The F statistic is a ratio of two variances. Sometimes we call it the F ratio. And here's right where the variances comes in. It's an analysis of the variance. Things aren't named by accident. And the statistician realized that by analyzing the variance, by calculating different kinds of variances, we could bring the effects of an independent variable or the group differences, we could make that visible, bring it to light. So the F ratio is the ratio of a between groups variance divided by the within groups variance. And we'll talk about both of these things down the road. But it's essentially this comparison of variances. So the way the F works is that we get two estimates of variance in the study. And think of the null hypothesis, right? If there's nothing going on, then there's nothing going on. The independent variable should not cause any differences. If it doesn't cause any differences, then it doesn't add to the variance. Because remember, variance is a measure of the differences. So according to the null hypothesis, these two variance estimates should be about the same. Now, one thing to remember about the F test is it does get us around this probability pyramiding problem, but it's what we call an omnibus test. It's not specific about differences. So all it tells us is that something is going on in the experiment. It doesn't tell us what it is. Right? When we did a t-test and we found a significant difference, we knew exactly what was going on. We knew that one group was higher or lower than the other in a way that was not related to chance. The F test only tells us something is going on. It doesn't tell us if one is higher or lower or which one it is that's higher or lower. Because remember, now we have more than two groups. So it's not specific in saying which group does the best, which group does the worst. It just tells us that there's a difference somewhere. If you think back to those three t-tests, right, the F test is kind of equivalent to doing all three of those at once and knowing if at least one of those tests would lead to the rejection of the null hypothesis. Let's make this concrete. So let's go back to that memory experiment example where I have three groups. Remember, it's rote rehearsal versus imagery versus sentence rehearsal. Now let's go further, right? In this design, I'm going to have, in this case, equal n. Each group has 15 people in it. It's not required for analysis of variance that the groups be equal, but in this case, it is. So there's important design things here that we'll need to calculate the F statistic and how to evaluate it. All right, one is large N, capital N, which is the total number of people in this whole experiment. So if you think of what we call the design of this study, right? I've got everybody who volunteers for my study, and I randomly assign them to one of these three groups. So there's 45 people who show up for my study, and they're randomly assigned 15, 15, and 15, right, to each group. Right, so uppercase N is the total N in the experiment, and we'll keep lowercase n to represent how much is in each particular kind of subsample. The other thing that matters here is the number of groups, and in analysis of variance, we represent that with the letter K, and in this case, K equals 3. Now, the very interesting thing about analysis of variance is that it is expandable, it's moldable, and it is an analysis that can can account for and analyze many different kinds of experimental designs. For example, K here, right? Number of groups, right? There's really no limit on the number of groups one can have in an analysis of variance. So I could have a fourth group or a fifth group or a sixth group or even 27 groups. The only real limit is human understanding. The other thing that is interesting about ANOVA is that it's expandable in terms of independent variables. In this demonstration, this sample, there's only one independent variable, memory strategy, that has 3 levels, right? K equals 3. I could introduce a second independent variable in this study, and it need not even be an independent variable. It could be something like class year. I could have one variable here be memory strategy, and then have another variable be seniors versus sophomores, right? So I would end up with 6 groups. For the seniors, I would have these 3 memory strategy groups, and then I would have, for the sophomores, also 3 memory strategy groups. So I could do an experiment with 2 independent variables, or even 3 or 4 variables. In ANOVA, we actually call them factors, not independent variables, because I could not randomly assign people to be a senior or a sophomore. I could randomly assign them to see verbs versus nouns in this experiment. And that could be a third variable. ANOVA is expandable that way, and there's some benefits for that we will get to down the road. But for now, this is called a one-way analysis of variance because there's a single variable, memory strategy. If we had 2, we would call it a two-way ANOVA, but this is a one-way ANOVA with one independent variable that has 3 levels, and that's the K. What I want to talk about in this design is these 2 variance estimates. So remember, right, variances are measures of the differences. And when we have this kind of design where we have 3 different groups, we can look at the variance or partition that variance in different ways. And the way to think of it is I could get the variance for everybody in the experiment. That's the total variance. And that would be regardless of which condition they were in. Right? I could say something like, right, the average performance in this experiment was 15 words, right? And that is everybody in the experiment. Similarly, in a class, right? In a class, I could say the class average, right? The class average was an 85 on the exam. But I could partition that class into different groups. I could say, well, here's the average for males. Here's the average for females. I'm taking that grand average and dividing it up according to some group membership or identification. I could say people on the right scored this on average. People on the left had this for mean, right? So whenever we have a large group, we could subdivide it. And that's what analysis of variance does, right? We subdivide that total variance into different kind of subgroups or different ways of looking at things and calculate these 2 variance estimates. The first one we're going to talk about is the within variance, right? So the source of variance is going to be within the groups. So here's an image of the design, right? Each one of those ovals represents a group. And as we've said, there's 15 people in each. And theoretically, right, we could get a mean and we can get a variance or standard deviation for each one of these groups. The within source of variance is a measure of the differences within each group. So what I would do, right, the way to think about this is if we're doing this, right, within variance, right, I would be looking, say, what's the variance for all the people, right? What's the variance for this group? What's the variance for this group? And what's the variance for this group? And effectively average them together. This would be like the pooled variance from independent samples, right? An average of the variances within each group. This is what we're going to call the mean square within. Now, mean square, MS, that is another way to talk about variances. Remember, the definition of a variance is it's the average squared deviation. Well, now think about what mean square means. Mean means average, right? So it's the average square. We call them MSs because even though they're variances, they're special variances, and we want to set them apart so they get a special name. So the way to measure, if we're measuring variances within the groups, we're going to call it the MSW, the mean square within. Right? Here's where we're not going to do stuff. I'm not going to have you calculate these things. I'm going to give these things to you at some level. We're not going to be dealing with the raw data, but still, I want you to understand this, right? The mean square within is measuring the variances within each group. It's a measure of the differences of the people in each group. So if we think of each group, right, each group is going to have a sample mean. Each group is going to have its own variance, and that variance is measuring the differences of people within each group. So let's think about exactly what that variance is measuring, right? It's a measure of differences. Well, what makes the people within each group different from each other? And right here's somebody, X1 in the R group, and let's think of somebody else, X2 in the R group, right? What makes these two people different? Why did they not score the same? Well, think of it this way. Would we expect them to score the same, right? Think of what makes people different on an exam. Why do you all not get the same exam score, right? You don't get the same exam score, and these people would not remember the same number of words because of individual differences. People are different. They eat different things for breakfast. They have different educational backgrounds. They have different motivation levels. And all of those things is what make us different, is going to lead to different performance. Right? Notice that's the same explanation for people within this group, within the I group, and also within the S group. Right? The people within each group are different solely because they're different individuals. The instructions are constant for each group, right? So the people over here, XR, X1R, and X2R, these two individuals, right, get the same memory instruction. Since it's the same memory instruction, that cannot cause differences between their performance. They're treated the same way. So the only thing causing differences within the groups is individual differences. This is sometimes called the error term or the error variance in analysis of variance. Let me see if I can write that. Where's my, right? The ERROR, because this is really measuring random error. This is essentially what we expect for differences when we get groups of people together. Right? This is what it says. If we get people together and do a memory experiment, we're going to expect them to be different. And the within subjects, within groups variance is this kind of baseline measure of differences. Right? This is what we expect, essentially, if the independent variable has no effect. We just expect people to perform and be different because they're different. The independent variable has no effect on this variance. It doesn't cause any differences between people within a group. Right, so this mean square within, right, just to come back to it, is like the pooled variance. We would get the variance within each group, kind of average them together. We call it mean square within. The formula, any mean square, like any variance, is a sums of squares divided by degrees of freedom. And if you look back at chapter 2 or 3, when we first did variances, right, we got the sum of the square deviations, divided it by n minus 1, and called it a variance. It's the same thing here. The mean square within is a variance. We take a sums of squares divided by degrees of freedom, and we get the mean square within. Now, the degrees of freedom for this particular variance, because it's a special variance, is a little bit different. The degrees of freedom within is n minus k. So in this case, right, we had 45 people, right? We have 3 groups, so there would be 42 degrees of freedom in this calculation. Don't worry about this SSW. We'll talk about that for in a little bit. But just remember, right? The mean square within is a variance, and like any variance, right, it's based upon the sums of squares and the degrees of freedom. Let's think about the other variance, right? We're going to partition the variance, the overall variance, into two pieces. We just talked about the within groups. The other source of variance is the between groups variance. And now I changed these to green because I want you to kind of get the difference that within and between are different. So now they're green, right? So this variance measures the differences that occur between groups, right? Why is somebody in the R group different from somebody in the I group? The things that make them different. And we're going to call this the mean square between, MS, mean square, and the subscript B for between. The mean square between, we said, is measuring these differences, right, between groups. So let's go back, right? Each group has a mean, each group has a variance, right? The variances are just measuring the differences within, right? Within. But this is between. So really we need to think, why is the mean for one group different for the mean for the other group? Why is someone who is in the R group have a different score from someone who's in the I group or someone who's in the S group, right? So let's think about this theoretically. What makes this person here, we'll call him X1, different from X2? Should we give them names? All right, we'll call this one, this is Timmy. And this is, who's this? This is going to be Sandy. Sandy's my dog's name. What makes Timmy and Sandy different from each other? Well, Timmy used rote rehearsal instructions. Sandy used imagery instructions. Right? They're also different individuals. Right? So, the mean square between, right? What makes people with between each group different? Well, first of all, individual differences. They're different people. Even if they're in the same group, I wouldn't expect them to get the same score. But now they have different instructions. So the independent variable is a likely source of variance between these two people, right? The mean square between is measuring differences that are caused by individual differences, which is always there, and the independent variable, which is sometimes there. Right, so the mean square between, when it comes to the math, is kind of parallel to the mean square within. We get a sums of squares and divide it by degrees of freedom. But in this case, the degrees of freedom is k minus 1. Right? K was 3, minus 1 gives us 2 degrees of freedom for the calculation of the mean square between. See how we partition the variances up, right? We look within the groups, we look between the groups. The independent differences is causing variance in both of those estimates, but only one of those has variability, measures variability caused by the independent variable. So by comparing these two variance estimates, we should be able to see if the independent variable is causing differences. And that is really, right, differences is what we looked at with the t-test. Are these two means different from each other? So now we can do that by looking at variances. So let's go a little bit further with that. Back to the F statistic, right? The F ratio. The F ratio is the mean square between divided by the mean square W, right? This is just what we told. We get these two variance estimates and then we compare them. But in this case, we compare them with division rather than subtraction. With the t-test, we compared the means. We said we're comparing means. We subtracted one from the other. Now we've got three means. We can't subtract three things from each other, but we can look at the variances and use division and come up with some conclusions. So what do we have? So the F then is the between groups variance divided by the within groups variance. Now what did we just figure out? We just figured out the theoretical sources of variances. The mean square between is measuring differences caused by the independent variable and individual differences, random error. Whereas the denominator, the within groups variance, MSW, is only affected by individual differences. Right? So theoretically, this is what the F ratio is doing. Right? The top part has two possible sources of variance. The denominator only has one potential source of variance. So let's think about what this does. Let's think about the case where memory strategy doesn't matter, right? If there's no effect to the independent variable or no effect of the factor that we're working with, right? Well, let's think what happens to the F ratio, right? So here's where we left off, right? The numerator is affected by two things, has two sources of variance. The denominator only has one source of variance. But if there's no effect of the independent variable, in this case, if memory strategy does not cause variability, that makes independent variables contribution effectively zero. So we have 0 plus individual differences divided by individual differences. Effectively, the independent variable goes away, and look what we have. We have a measure of individual differences divided by a measure of individual differences. Now, since we're measuring these differences in the same individuals, we would expect these two things to be pretty much the same. And what happens when you divide a number by itself? You get a 1, right? In this case, when there's no effect of the independent variable, the F ratio should be close to 1. This is like when we did a t-test, right? If there was no difference and you subtract 1 from the other, you get a 0. Well, if we had put those two means and divided, we would expect a 1, right? Any number divided by itself is a 1. So this is the basis of the logic of the F test. We examine the F ratio to get a sense, right, of the size, the contribution to variance of the independent variable. If it's a 0, we should see an F ratio of about 1. So let's go next. What if there is an effect of the independent variable? Well then, right, the F ratio is the same thing, two sources divided by the single source. And in this case, the independent variable is greater than 0. It's contributing to the variability between groups. So that means the numerator is going to be something larger than the denominator. The contribution to the independent variable is something greater than 0. So in this case, we'd have a large number divided by a smaller number would give us an F ratio of something greater than 1. So with putting these last two slides together, right, by looking at the F ratio, we can make an inference about the contribution of the independent variable. If it causes differences, that's variability, we can measure it. It'll make the numerator larger than the denominator, and we will get an F ratio greater than 1. If it doesn't, then we effectively have two different assessments of the same individual difference. They should be about the same, and they should equal 1.